Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will emphasize and ponder on one discussion which is related to dielectric. A dielectric is nothing but an insulating substance, and this substance gets polarized when placed in an external field. Now, we have also discussed that when you have a capacitor, a parabolic capacitor, which is having some polarities, positive and negative, then if we keep some insulating material inside, this type of insulating material which is kept in between the plates, okay, in between the plates of a capacitor, in between the plates of a capacitor is called a dielectric. It is called a dielectric. So we have to understand and let us collaborate, okay, on some of these terms. That means when we place these dielectric materials inside a substance or inside a capacitor, it will get polarized. Okay, polarization is nothing but the phenomenon in which the molecules will split into their positive charge and will split into their negative charge. Now, there are two types of dielectrics. Number one is what we define as the nonpolar dielectrics, and the other is what we know as the polar dielectrics. So these nonpolar dielectrics, okay, these examples of nonpolar dielectrics will be such as nitrogen, okay, such as these hydrogen, okay, and some and also these alkenes, a group of alkenes, like for example CH4, C2H6, and so on and so forth. Okay, CH4, C2H6. These are groups of what? Non-polar molecules. And what are non-polar molecules? Non-polar molecules are those type of non-polar dielectrics, are those type of dielectrics in which the center of the positive and the negative charge of an atom, they will coincide. Now, when you take for example, suppose like H2, okay, I have this molecule of H2, and over here, suppose these are our H2 molecule. These two spheres represent hydrogen atoms, and both these spheres, if I draw only the that structure of hydrogen atom, that means this will be our hydrogen atom, and this bond will give me our negative. And we know that these hydrogen atoms will be positive, and hydrogen atoms also will be positive, which means that the center of the positive and the negative charge, they will coincide, which means that over here lies the center of positive and negative charge. Okay, likewise, then over here, suppose let us take when we have this dielectric, which might be hydrogen, which might be nitrogen, that means they will have all these atoms. All these atoms over here, we define them as domains. Okay, all these atoms, we define them as domains. Okay? Domains. So each individual atom will have the corresponding positive and the negative end. So all these positive and negative end, it will be in this form. It will be in that form. Okay, and which means that if I draw a sphere like this, a circle like this, the center will always be the same. It means over here you will have only that center. This is the center of that sphere. This is the center of that sphere. This is the center of that sphere. This is the center of that domain. All it will be having the same center. And besides that, okay, all these, there will be positive and negative charges due to the domains or due to the atom. There will be positive and negative charges due to the domains or due to the individual atom. Okay? Due to the domains are nothing but atoms, individual atoms contributing in atoms. We will have negative charge as well as positive charge. Likewise over here, that means you will have positive and negative, negative and positive, negative and positive, okay, positive and negative, negative and positive, and so on and so forth. So all these will form our domain. But when you have a dielectric substance and if there is no electric field, that means when E is equal to 0, that means absence, okay, absence of electric field. What will happen in the absence of an electric field? Okay, in the absence of an electric field, the dipole moments, okay, the dipole, there will be no electric dipole moment. In the absence of an electric field, in an absence of an electric field, there will be no electric, there will be no net electric dipole moment. Okay, there will be no net electric dipole moment, which means that since these dipole moments are in random direction, there will be no electric dipole moment. And if there is no electric dipole moment, what happens? This is because that all these atoms are in random direction. Okay, are in random direction. So if these individual atoms are in random direction, there will be no electric dipole moment. There will be no electric dipole moment under the condition or under the consideration that if electric field is 0 or in the absence of an electric field. So what happens when you take this dielectric and then you place it in between the plates of the capacitor where electric field lines can pass through? When you place these this dielectric inside the plates of capacitor having electric field E, that means having electric field E, what will happen? All these dipole moments, there will be a momentary increase, okay, a momentary creation. The moment when you pass electric field on a dielectric, when you pass electric field on a dielectric, what will happen? When you place this dielectric, when you place the dielectric in the presence of an electric field, when you place the dielectric in the presence of an electric field, what will happen? All these domains, all those domains, they will align in the field direction. They will align in the field direction. Now, when they align in the field direction or in the direction of our applied electric field, there will be a creation. Okay? There will be a creation of these temporary dipoles. We call as temporary dipoles or dipole moment. Okay? Dipole moment is a temporary creation of temporary dipole moment. So all, which means that the positive charge will be in the direction of the applied field. The positive charge will be in the direction of the applied field, and these negative charge will be in the direction which is opposite to the field. Okay? So in this case, which means that the positive charge and the negative charge, the positive charge will be in the direction of E, and this negative charge will be in a direction which is what? Which is opposite to E. Okay? Opposite to E. So positive charge in the direction of the electric field, positive charge in the direction of the electric field, and negative charge, all these negative charges will be in the direction which is opposite to E. So I have represented all these positive charges in the direction of the applied field. Whereas in this direction, all these charges are in different direction or in random direction. And over here, the negative charges are in the direction which is opposite to the field. Okay, the negative charges are in the direction which is opposite to the field. So when there is when this dielectric is in this form, that means there is a momentary creation of temporary dipole moments. Okay, temporary dipole moments, so long as the electric field is applied across the dielectric. So over here, I have put a condition that E not equal to 0. When E is not equal to 0, that means it is in the presence of the electric field. Now some examples over here, like if I consider the case of a carbon dioxide molecule. Okay, a carbon dioxide molecule. A carbon dioxide molecule a carbon dioxide molecule, CO2. Okay, CO2. That means the formula will be in this form. Okay, the formula will be in this form. We have C, and there are some double bonds, and we have the oxygen atom, and all these oxygen atoms will be having these lone pairs of electrons, which means that over here it will be rich in electrons, whereas this carbon will be deficient of electrons. So this will be delta positive, delta negative, and delta negative. Carbon will be having charge deficiency, whereas oxygen will be having a more number of charges, rich in electrons. Okay, rich in electrons. So that is why over here, if I have a carbon atom and all these are your oxygen atoms, which means that over here, even the center, there is a momentary, the center of the positive and the negative charge, they will go inside. Okay, so from here, this is very, very clear that for non-polar molecules, when you pass, when there is the presence of electric field, what will happen? In the presence of an electric field, the dielectric, when the dielectric is placed in the presence of an electric field, what will happen to the dipoles? The dipole will align in the direction of the field. And when the dipole align in the direction of the field, what will happen? There is a creation of temporary, okay, not temperature, temporary dipole moments. And these are temporary dipole moments. The creation of these temporary dipole moments will be in such a way that the positive charge, that the positive end of the dipole will align along the field direction, and the negative or end of the dipole will align in the direction which is opposite to the field. Okay, opposite to the field. And from here we can also make one point of concern, or one point of consideration, that this end of the dielectric will be having the charge density which is positive in charge, so it will be having a delta positive, whereas this end of the dielectric or the substance where we have all these negative charges, it will be having a charge density which is minus sigma. All these plus sigma and minus sigma are induced, okay, induce charge density, okay, induce charge density. The induced charge density will be possible only if we supply electric field across a dielectric, okay, across a dielectric. Now let us move on into polar dielectrics. In these polar dielectrics, when you talk about the word poles, that means there is from the word itself, poles, that means you'll be having one end, there will be positive as well as negative charges. In polar dielectrics, the center of the positive and the negative charges are separated by a finite distance. Okay? Separated by a finite distance. So some examples of these polar dielectrics, okay? Some examples of these polar dielectrics will be like HCl. Okay? Some examples like of these polar dielectrics will be HCl, and then a molecule of water, okay, and then there's ammonia, which is NH3, okay, ammonia, which is NH3, and also we have different types of alcohols, okay, different types of alcohols. Alcohols are nothing but are compounds whose functional group is OH, okay, is OH. So all these types of substances available in nature are will behave as polar molecules, or we talk of the substance as a polar dielectrics. So which means that the center of the positive and the negative charge are separated by a finite distance. That means there is a finite distance between them. Now let us consider the case of hydrogen molecule before we move on into the details of that. Suppose if this is our chlorine atom, if this is the center, this is our hydrogen atom, and suppose if this is our chlorine atom, and from here it is evident that that is the bond, this is the bond, okay, HCl, okay, HCl. Now H will be having delta positive, and Cl will be having delta negative. So that is the positive end, that is the negative end, and there is some distance. Okay, there is some distance or dipole length. So from here, this will be the negative end, and this will be the positive end, and there is some distance between them, which is the dipole. Okay, length of the dipole or dipole length. Okay, length of the dipole or dipole length, length of the dipole or dipole length, length of the dipole or dipole length, which means that these two atoms will be separated by a finite distance. So from here, we know that since these are forms, these are examples of electric dipoles. These are examples of what? Electric dipole. So when these are examples of electric dipoles, so one end will be having positive and one end will be having negative. One of the atom will behave as negative and one of the atom will behave as positive. So from here, it is evident that there will be a electric dipole moment denoted by P. Okay, electric dipole moment. So always the electric dipole moment is directed from negative to positive. Okay, even in this case, suppose if I consider the case of water molecule. Okay, if I consider the case of a water molecule, like over here, suppose if this is your hydrogen atom and this is our oxygen atom and this is our oxygen atoms, and if we draw nicely, that means over here we have this H hydrogen atom. Okay, all those are our hydrogen atoms, and these are our oxygen atoms. We have these lone pairs of electrons, and over here this will be delta negative, delta negative, okay, delta negative, delta negative, and on hydrogen atom you will have what? You will have this will be delta negative, and over here this will be delta positive, which means over here this will be the hydrogen atom will be the positive end and the oxygen atom will be the negative end. The oxygen atom will be the negative end, and from here there will be some bond. Okay, there will be some molecular bond, and this molecular bond will give us our what? Dipole length. There will be some dipole length. So which means from here the direction of the electric dipole moment is always directed from negative to positive. The direction of the electric dipole moment, okay, P, is always directed from negative to positive. Okay, from negative to positive. So this is the way how these molecules will be treated as polar molecules and non-polar molecules. In polar molecule, you will have negative charge and positive charge separated by a finite distance. This finite distance is nothing but the dipole length. Okay, dipole length. So from here, when you have these types of dielectric substance, and over here, suppose in the absence of an electric field, I have this. When E is equal to 0, that means electric field is 1. Electric field is absent. In the absence of an electric field. In the absence of an electric field, what will happen? We find out that there will be positive and negative charge, but there is some distance between them. There is some distance between them, which means that over here, center of positive and negative charge does not coincide. Okay? Does not coincide. Okay? In polar molecules, the center of positive and negative charge, they do not coincide or does not coincide. They do not coincide. Then over here, all these electric dipole moments will be in a direction which is in random when the electric fields are in, when you don't pass any electric field inside the dielectric material. So from here, all these domains or atoms are in different direction. Okay? All these domains or atoms, okay? All those domains or atoms in the absence of electric field, when there is no electric field, or E equal to 0, all these atoms will be in the state of what? In the state of random, okay? Random direction. Or when all these atoms are in random direction, it means that all those the net dipole moment will be 0, which means they will cancel each other's effect. Okay? The net dipole moment will be equal to 0 in the absence of an electric field. Now, for instance, over here, if I have if I take this dielectric and then place between the plates of a capacitor, okay, and then place between the plates of a capacitor, that means I have this plane, okay, I have this plate of the capacitor, and then these are the plates of the capacitor. Okay, these are the plates of the capacitor. And then I'll take this dielectric and then keep in between the plates of the capacitor. Okay, and I'll take it in between the plates of the capacitor. What happens is that all these electric dipoles, okay, they will align along the field direction. Okay, they will align along the field direction. All these electric dipoles, they will align along the field direction, which in this case, if this is positive, if this plate of the capacitor is positive, and if this plate of the capacitor is negative, which means that the electric field is not 0. The electric field is not 0, which means that this takes place in the presence of an electric field. In the presence of an electric field, all these dipoles, they will align along the field direction. All these dipoles, what will they do? They will align along the field direction. They will align in the field direction in such a way that if this is positive and this is negative, that means the direction of the electric field lines will be in the direction from positive to negative. And in the presence of an electric field, all these dipole moments, number one, they will align along the field direction. The positive end of the dipole will be along the field direction. Positive end of the dipole will be along the field direction, whereas the negative end of the dipole, these negative end of the dipole will be in a direction which is opposite to E. Okay? Negative end of the dipole will be in a direction which is opposite to E. But all these dipoles are aligning along the field direction, in the same direction, aligning in the same direction of the field. Then, if they are aligning in the same direction of the field, that means the net electric dipole moment, the net electric dipole moment will not be equal to 0. Okay? The net electric dipole moment will not be equal to 0. The net electric dipole moment, will not be equal to 0. So there will be some electric dipole moment. Okay? Some electric dipole moment. And from here also, we have discussed that when you have this dielectric and when you place in between the plates of the capacitor, what happens? What happens to the dielectric? All these dipole moments, all these domains or dipole moments, all those domains or dipole moment, they will get polarized. Okay, they will get polarized. All those domains or dipole moment, they will be polarized. And when they get polarized, that means these positive and negative charges will be separated to a finite distance, and which means that this end of the dielectric will be having a net. The surface charge density will be sigma, plus sigma, okay, plus sigma. All these, only this space, only this edge, okay, only that surface, only that edge of the dielectric will be having a net negative charge density, and over here the net positive charge density, and over here this will be having net negative charge density. Over here minus sigma, over here minus sigma, over here also minus sigma. So there will be induced, okay, there will be induced surface charge density, surface charge density. So when you apply electric field in a dielectric, the dielectric will get polarized. When you apply electric field in a dielectric, when you apply electric field in a dielectric, what will happen? The dielectric will get polarized. Okay, the dielectric will get polarized. This dielectric will get polarized. That dielectric will get polarized. And when it gets polarized, it means that there will be creation, okay, creation of these induced, okay, induced charge density, okay, induced charge density, induced charge density. All these which I've written as plus sigma and minus sigma. All these plus sigma and minus sigma are nothing but sigma I, okay, which is our induced charge density. And due to this induced charge density, there will be these, it will give rise to the total or net electric dipole moment. Okay? Net electric dipole moment. Net electric dipole moment. So these are some of the important features related to dielectric and style. So there are two types of dielectric. Number one is nonpolar dielectrics, where the center of the positive and negative charge does not coincide. And in polar dielectrics, we have the center of the positive and negative charge are separated by a finite distance. Just go through the lecture so that you will understand the whole concept. Thank you.